Hello, my name is Devshi Das and co-presenting with me today is Noble Saji Matthews. We are delighted to present our research paper titled Exploring Security Vulnerabilities in Competitive Programming, an Empirical Study at the esteemed East 2022 conference. Let us dive into our main motivation for this study, security. Developing secure and reliable software systems has become integral to software development over the past years. Strong efforts toward building secure software systems have been driven by significant financial losses incurred in the past, as well as concerns about the security of critical systems. To prevent the introduction of insecure code in code bases, we need to identify insecure coding practices among developers and work towards either improving the system to better handle common vulnerabilities or educating the developer about the same. Identifying vulnerabilities as soon as possible and addressing them is critical, but the more desirable solution is to prevent vulnerabilities in the first place. Previously, security was a secondary concern, functionality being the primary one. However, according to the modern approach, security should be integrated into every step, right from the initial design to the final details of implementation. Inculcating secure coding practices and widespread awareness about the same is a paramount way to go about this. To help with identifying and ameliorating software vulnerabilities, there are multiple ways to catalog and define them. The Common Weakness Enumeration, or CWEs, maintained by Maitre, is a community-developed list of the most commonly occurring software security weaknesses found in real software. The Common Vulnerability Scoring System, or CVSS, provides a score reflecting the severity of the vulnerability depending on its characteristics, the environment in which it occurs, and its endurance over time. These listings and coding standards help with researching security issues and defining solutions. Studies show that most of the vulnerabilities detected in real-world software can be avoided if secure coding practices are followed. Unfortunately, however, insecure coding practices are widespread in the software community today. There have been studies in the past that have shown that vulnerable code is rampant in open source code bases and even finds its way into production code. To understand developers and prevalent practices, past works have looked into public repositories and online question and answer platforms as sources of information. There are some studies that show that software developers often lack the required knowledge about security. Similarly, students aspiring to be developers are also largely lacking when it comes to a good understanding of writing secure code. Clearly, we need to build a better system that helps programmers adopt good coding practices and make them aware of the key issues right in the learning phases.
Now this is where CP, or competitive programming, comes in. So let's begin with what is CP. Competitive programming, or CP, is a practice with well-defined problem in which contestants have to develop programs that clear all the test cases as well as satisfy the time and space constraints. CP is often practiced with the intent of learning how to code in a particular programming language, developing a better understanding of data structures and algorithms, writing efficient code, and writing it fast. The contestants are ranked on a leaderboard based on their solutions and submission time. Knowledge of algorithms, data structures, and time complexity are the focus points of competitive programming. CP has been around for quite a bit, and there are several popular CP platforms such as CodeForces, Topcoder, and CodeChef. There are also several international competitions that make use of CP, such as ACM ICPC and Google CodeJam. What brings competitive programming into notice when it comes to software development community is that in recent times, many job placements and hiring tests have CP format-based evaluations. Many well-known software companies have competitive programming style screening tests which encourage students across the globe to practice CP regularly. CP is used by many to learn and practice how to code. Many software developer aspirants also practice CP regularly. We now see what CP is, but why is CP relevant to our discussion? CP data is a rich source of information about coding practices, which has not been previously explored from the perspective of insecure coding practices. It can give us several insights into insecure coding practices, as it gives us information about how the programmer practices change over time, how various contest parameters can affect the number of vulnerabilities introduced, and which language artifacts are most prone to vulnerabilities. Through this exploration of CP data, we wish to highlight that something as critical as secure coding should not be added as an afterthought in learning programming or in developer recruitment. Instead, learning avenues like CP could motivate users to learn more about security and help reduce the steepness of the learning transition from a programmer to a software developer. Let us quickly go over the research questions we proposed and explored in this study. We begin with some fundamental questions, such as how prevalent are security vulnerabilities in CP data, and what kind of vulnerabilities and insecure coding practices can be found in CP data. Even though the relevance of CP is increasing in the software industry today, there is a distinct lack of empirical research on CP data, especially from the perspective of insecure coding practices. We investigate if the prevalence of security vulnerabilities in CP data is concerning. Accordingly, we explore the empirical relations between the number of vulnerabilities per submission versus the leaderboard position. The main incentive in CP is ranking well on the leaderboard. That is why we try to understand whether or not incentive systems could encourage secure coding practices. We notice that many programmers submit solutions to the same questions multiple times, even after scoring the maximum possible score. We decided to investigate this and try to ascertain if the reason for doing this was to improve the code or to remove vulnerabilities. Finally, we tried to investigate the ultimate highlight of this work. Does CP inculcate insecure coding practices in programmers? Hence, our final research question is, do contest participants consistently write insecure code? If we find that the answer to this question is positive, then we have a point of concern, and the software community would want to take notice of this aspect.
Before we go further into vulnerabilities and the insights we can derive from CP data, let us go through how our exploration was structured. Here is the workflow diagram of how we performed the analysis using two static analysis security testing or SAST tools. We used data supplied to us by CodeChef, which is one of the most popular competitive programming platforms. The data consisted of 6.1 million submissions pertaining to 85 contests that were held over the year 2020. The chart shows the top 10 most popular languages used on the platform. Of these submissions, we worked our analysis only on the submissions written in C++14 and C++17 that were graded 100 out of 100 by the online judge. A submission scores 100 if it compiles and clears all the test cases within the given time and memory constraints. We reason that if we can find vulnerabilities in this apparently correct and acceptable code, we can assume that the situation of submissions that do not score 100 will be similar, if not worse. After the pre-processing steps, we were left with around 700,000 submissions. We explored the vulnerabilities using popular SAST tools, Parasoft C++ Test, and PVS Studio. PVS Studio classifies all the detected vulnerabilities according to certain vulnerability IDs or VIDs using pattern matching, symbolic execution, and data flow analysis based inference algorithms. We explored the CWEs associated with the detected vulnerabilities and manually filtered the results to remove instances that are not relevant to our study or cannot be classified as vulnerabilities in the context of CP. For example, certain issues flagged by PVS Studio are possible typos, which are not security vulnerabilities, just probable logical errors. We assume that the submissions have no logical errors since they have passed the test cases that were solely designed to thoroughly test the logic or functional correctness of the code. The results of Parasoft C++ test were used to verify the results obtained from PVS Studio and to generate compliance reports. We check compliance with the CWE Top 25 plus on the CUSP 2019 configuration, 28 of which are relevant to CPP and implemented using 81 rules internally. Let us now go over the results that we obtained from the analysis. How prevalent are security vulnerabilities in CP data? We found that 394,051 or 56.8% of the submissions were flagged by static analysis. However, all such issues flagged by the SAST tools need not correspond to security vulnerabilities as previously mentioned. Hence, after the manual review, 144 vulnerability types out of 246 detected were chosen based on the possible consequences that they could introduce in real-world software projects. This was done based on the detailed official CWE and PVS Studio documentation. We found that 34.2% of the submissions were flagged with vulnerabilities and that the average number of vulnerabilities per submission was about 1.8. We also used Parasoft C++ test to analyze the dataset's compliance with the top 25 CWE plus on the CUSP 2019 list as a security standard. Compliance testing of the dataset resulted in 10 out of the 28 CWEs being violated, which accounts for 64.3% of compliance. The severity of the vulnerabilities as reported by the toolkit is depicted in the figure. 47.32% of the reported vulnerabilities are ranked as belonging to the high or highest severity level. The next research question we posed was, what kind of vulnerabilities and insecure coding practices can be found in CP data? To answer this question, we extracted the CWEs associated with the flagged issue IDs from the official documentation. The figure shows the distribution of the various types of vulnerabilities. The vulnerability with VID V1010 is the most frequently occurring vulnerability according to the PVS Studio results. It has 168,395 occurrences, and it corresponds to using unchecked tainted data in a critical expression that could lead to security issues. The CWEs associated with the patterns that raise this flag are CWE 134, 138, 20, and 78. CWE 134 highlights how an externally controlled format string can result in information disclosure, which makes the program easier to exploit. It can also allow an attacker to modify memory and execute arbitrary code, compromising the system's security significantly. V1003 and V1059 have no CWE associated with them, but they are a common class of problematic patterns related to defining macros in C++ that could lead to many unforeseen errors, significantly reducing the reliability of the code. This table here shows the most frequently flagged CWEs as reported by Parasoft C++ test. According to the official CWE documentation, many of these identified vulnerabilities can cause security concerns, leading to issues such as denial of service, unauthorized memory access, bypassing access control measures. The remaining undermine the security of the system indirectly and reduce its reliability. The other table here shows the major consequences associated with the most frequently detected VIDs.
Moving on to RQ3, does the leaderboard position of the programmer show any correlation with the number of vulnerabilities? The leaderboard position on most CP platforms depends not only on the score, but also on the time taken to solve and submit the solution. Hence, it's reasonable to assume that coders try to solve and submit their solutions as fast as possible. There is no incentive in the leaderboard scoring rules for writing secure code. We try to investigate if there is any correlation between leaderboard position and the number of vulnerabilities in the submissions, to try and gain insights into whether this scoring scheme encourages insecure coding practices. We obtain a Spearman correlation coefficient of -0.066, which indicates that there is no clear correlation between the leaderboard position and the number of vulnerabilities in the submissions. We also conclude that the highest ranking submissions are not necessarily those with the least vulnerabilities. Hence, the current system has no real incentive for writing secure code, and its effects are clearly visible in these results. We observed from the data that users often submit solutions to the same questions multiple times, even after scoring the maximum possible marks. Hence, in RQ4, we pose the questions: do programmers improve on code security after securing a perfect score? Making repeated submissions does not help with positions on the leaderboard, and they cannot improve on the timestamp associated with their first successful submission. Hence, the reasons behind repeated submissions could be that the programmer is trying an alternative approach for personal learning reasons, or he could be trying to improve the efficiency with respect to time or space complexity, or just trying to clean up the code to make it more readable. We tried to investigate if any programmers were trying to remove vulnerabilities or improve the security of their code while making repeated submissions. Hence, we plotted the number of vulnerabilities per submission for the most highly repeated submissions and found that there was no real decrease. Hence, we concluded that the programmers do not try to reduce the number of vulnerabilities in their code even while making repeated submissions. Do contest participants consistently write insecure code is the last research question we discuss. The main motivation for investigating CP data stems from the fact that in recent times, practicing CP helps clear job placement tests for software developer positions. If practicing CP consistently encourages the adoption of insecure coding practices, it would be an interesting and concerning point to notice. Hence, we wanted to investigate if programmers consistently repeat insecure practices over long periods of time. We selected 10 of the most consistent users who participated in competitions every single month and plotted the average number of vulnerabilities per submission for each of the 10 users for all the 12 months in order as shown in the figure. We observed no consistent decrease in the number of vulnerabilities detected for most of the users over time. We also evaluated the number of times the same error is repeated by a user for the entire dataset. We also record that a programmer repeats a unique vulnerability 20 times on average, although this figure shows high variability with a coefficient of variation of 2.7 over the entire dataset. Repeating the exact same insecure practices so many times could indicate a lack of understanding about certain secure coding practices or a strong disregard for secure coding habits, which is a point of concern we would like to raise through this study. We now move on to the last phase of this presentation, conclusion and future work. We investigated 6.1 million submissions of CP data to try and understand the prevalence and nature of security vulnerabilities. We used static analysis tools and manual review to identify and report that 34.2% of the submissions contained vulnerabilities. We also consolidated these detected vulnerabilities according to the common consequences listed by the associated CWEs to highlight the potential dangers that they possess. We found no conclusive correlation between the leaderboard position and the vulnerabilities in the submissions. We also investigated if people who make repeated submissions after obtaining a perfect score improve the security of these submissions, and we found the contrary. We observed that the subset of data corresponding to consistent CP programmers and the average number of vulnerabilities per submission show no sign of declining. As discussed in the preceding sections, all of the above inferences are reasonable because CP scoring systems have no real incentive for writing secure code. Hence, in conclusion, through our study, we demonstrated that CP does not necessarily encourage secure coding practices among programmers. Our conclusion is increasingly concerning, and not only because CP has become extremely relevant in recent times as part of job placement tests, but also because many novice programmers use CP platforms to learn and develop programming habits. Further work needs to approach this concern from different angles to assess the concern and address it so that the overall awareness about code security can be improved among developers. User studies and surveys can be conducted with regular CP practitioners to understand how to better impart secure coding practices. We suggest long-term experiments with modified CP scoring rules that include penalizing insecure coding practices. The proposed system could encourage even novice programmers who use CP to practice their skills to inculcate secure coding practices right from the beginning. We would like to thank CodeChef for providing the competitive programming dataset and PBS Studio and Parasoft for providing us access to their tools for the purpose of this study. For more details, please refer to the paper. Here is the link to our lab, the Research in Intelligent Software and Human Analytics Lab at IIT Tirupati, and we thank you for your attention. Thank you.